Everybody, and welcome to class on Victory Wednesday. So today we're going to cover section 3.6, the method of variation of parameters. I will try to make this as brief as possible because it's boring to watch a long video. So the point of today is to solve the same kind of equations we were solving in section 3.5, but using a different method, this time using a method that always works, even if there's not an exponential or a trigonometric function here on the other side. So this method works as long as what's on the other side is continuous. That's the only condition you need. Now this technique, this method has drawbacks. So one of the learning goals of this section is understand when what we did last time is more appropriate than what we will do this time and vice versa. So recall last time the big theorem. If you want to solve, so equation 2 is this, recall that from last time. If you want to solve that, then what you first do is solve that equation but with a 0 on the other side. So here's the familiar stuff. And then to finish off, you just have to find a single function that solves the original equation and slap it right there, and you are done. So last time we talked about how the method of undetermined coefficients is a way of getting at this y of t, this single solution that solves equation 2. And as we talked about last time, the word method here is used loosely because really the methodology, despite its fancy name, is just guessing. So you make a guess, hope it works out, and if g of t, this function on the other side, if it has a nice enough form, like a sine or an exponential or a multiplication of those two things, you can make a reasonable guess and get it to work out. So the question is, what if what's on the other side is not sine or exponential? And what if we don't want to guess? What can we do? Well, there's a method that always works in principle. Before giving you the method, I need a definition and some notation. So the Wronskian of two functions, y1 and y2, denoted w, y1, y2, is this. First function times derivative of second minus derivative of first times second. It's like a product rule kind of setup, but with a minus in between. Don't worry about where this comes from now. If you want to see why this is relevant, you can read the text. Here's an example. The Wronskian of e to the 5t and e to the 7t is, here's the computation, and it simplifies to 2e to the 12t. Now the formula here is not super relevant. You can just ask Wolfram to get this for you. There's some nice theory here from linear algebra. Those of you who've had that will recognize this as a determinant of a 2x2 matrix. You don't have to recognize that, of course. So if you go to Wolfram and say Wronskian, it's going to help me here. Wronskian, here's the format I like. Wronskian of function 1, function 2, hit enter. So Wronskian of, separate the functions with a comma, and it says here 2e to the 12t, what's on the slide. So you can use Wolfram to get Wronskians for you if you want, and save yourself a little bit of computation there. Okay, here's the method. So this is a method for giving you a solution, this capital Y of t of equation 2. And I should say here the book demonstrates this method for a much larger class of functions. This methodology works, though, only if there's a leading coefficient of 1 on the y double prime. So if you don't have that, you should divide by whatever's here. So if there's like a 5y double prime, then divide everything in sight by y. Right? So you want a leading coefficient of 1. Otherwise, this formula won't quite work. So that's in contrast to last time. Last time, it didn't matter if you had a 2 up here. But for this time, you would divide by this coefficient. Okay, anyway, so if y1 and y2 are like last time, those non-redundant solutions of the homogeneous equation, so y1 and y2 are, e to the t cos 2t, e to the t sine 2t, whatever. And once again, we do need g of t to be continuous. Then here's a general formula for that y of t. So here's just a formula you can use, no guessing. The formula, as you can see, is kind of gross. You have to take integrals of fractions, always dicey integrals of fractions. Also, if you read this in the book, it has some more notation surrounding it. But the notation is just saying, when you do this integration, set the constant to 0. So there's no plus c, or there is a plus c and c is 0, if you like. So the general solution to an equation like this is this. So here's your homogeneous stuff from your first exam, and then here's just a big old capital Y of t right there. So there you go. No guessing. Here's an example. Okay, so first you solve like you do on your first exam, r squared plus 4. This gives solutions of plus or minus 2i. There's no real part, so there's like an e to the 0t here, e to the 0t if you like, but you get purely trig functions here because the solutions here are purely imaginary, plus or minus 2i. So now the real work is finding this capital Y of t. So okay, first we have to find the Wronskian to put down there. That's why we needed the definition of Wronskian. So let's do that first. So if you go to Wolfram and ask, what is the Wronskian of cos 2t sine 2t, like I just did a second ago. So if you'd like to see that again, Wronskian of, and the formula is symmetric, so it doesn't matter the order in which you write anything. You just have to be consistent about it. So 2, there you go. That's why there's a 2 down there. Okay, so minus y1. See, there's minus y1. Right? I can't put this all on the same slide at the same time, but minus y1. Whoop, wrong way. And then here's y2. And then here's g of t. Well, there's g of t is 3 cosecant t, so I split the 3 in the cosecant. Here's y2 divided by the Wronskian, plus the other function from the homogeneous part, and then again your 3 cosecant t, and there's your other homogeneous solution, and then again divided by the Wronskian. And there you go. This is the general solution to this original DE. Now, as always, if an answer has like an integral in it, it would be nice not to have the integral in it. So here you go. Here's the answer without the integral. Now, integrating sine 2t cosecant t or integrating cosine 2t cosecant t, as you can imagine, that might be kind of obnoxious. Your book will show you the steps here if you'd like to see them. As you might guess, it involves the double angle formula. So you unpack sine 2t, unpack cosine 2t, and it turns out this entire integral right here, this piece is just 3 sine t. That's nice. This integral here, it turns out, is 3/2 and then like this stuff. So not quite as nice. So, there you go. Now, as you might expect, making a differential equation more complicated will give you more complicated solutions. This is a pretty complicated equation, despite its smallness up here. You're looking for all functions whose second derivative plus 4 times themselves is 3 cosecant. And cosecant is not a particularly nice function. It's not particularly tame. So it turns out, if you want all such functions, here they are. Sums of cosine 2t and sine 2t minus, and then all this stuff, right? So if you want to, and I don't think you do, but you could fix values of C1 and C2. So put like a 1 and a 1 in there if you want, and then take this entire thing and plug it in up here. And it turns out you will get, after applying, no doubt, many trig identities, you will get 3 cosecant t. So there you go. There's the method. So it's just a formula. Now, I should have said this earlier. You don't have to memorize this formula. You just have to know when to use it. So you'll be given this on an exam. You shouldn't spend time memorizing it. Okay, let me show you one more. So now we have, again, the same setup. So something familiar, but now we're targeting something that I guess looks exponential because it's e to a function. But when I say exponential, I mean e raised to a linear function. E to the 8t, e to the 9t plus 1, whatever, things like that. So e to the t squared is much different when you have a quadratic function up here. So in particular, this function, its derivatives don't look much like itself. Because when you start taking derivatives of this, the chain rule pops down like a 2t. And now you have linears times the e thing. So the derivatives are too different to try making a guess. So we don't make a guess. We ask Wolfram to solve the homogeneous part. And so here's the general form of things. E to the negative t, and then cosine and sine root 2t falls out from this. Okay, so now we need the Wronskian of those two things. You just type it into Wolfram, so I'll spare you doing that. But there you go. There's the Wronskian. And now you just crank out that formula. Minus y1, and then here's y2 up here. There's the g of t function, Wronskian, and so on. Now, at this point, you'll notice the slide doesn't keep going. In contrast to the previous example where I had integrals here and then like gave an answer without integrals. As you can imagine, and I don't think you need a particularly active imagination to realize this, these integrals are not doable. So if you go to Wolfram and say, hey, what is that? So let me show you what it says. So integrate. Okay, where is it? So e to the negative t times sine square root 2t e to the t to the second divided by square root 2 e to the negative 2t. Okay, integrate that. Let's see what Wolfram says. It says this. First of all, look at all the i's. So what are we supposed to do with that? But also it contains this this function that I'm sure you've never seen before. ERFI, E-R-F-I. ERFI is the imaginary error function. So what Wolfram is telling you is that basically it can't do it because some functions don't have antiderivatives you can write down. It's basically saying, look, I've created a word, or somebody created a word to represent part of this integral, but it's just a word that says I can't really tell you anything. So if you see something like this, you of course just give up. Like some integrals aren't doable. It's not hard to believe, I think, looking at this particular integral, that it's not doable. So you just have to leave your answer like this. And it is what it is. So as we're starting to see, the theory of differential equations can be quite difficult. So this differential equation here, to me, doesn't look so bad. The left-hand side is linear and there's just constants, 1, 2, 3. The right-hand side is not quite exponential, but it's pretty close, like e to the t squared. Is that really that much worse than e to the 2t? It turns out, yes, it is much worse. So even though this looks like kind of a dinky little thing, non-threatening, the solutions are quite monstrous. Like the solutions you can barely even write down. You have to write them down in a non-satisfying way with these integrals you can't do. So you got to be careful with differential equations. Like again, if this was supposed to be a 2t, but you messed up and wrote a t squared, all of a sudden the problem is much harder. So differential equations are unstable in this respect. Differential equations that look a lot alike could have wildly different solution sets and can have much different levels of difficulty to solve them. Okay, so to conclude this section, why would you do method of parameters, a variation of parameters? Because in principle, and a lot of stress on that word, in principle, it always works. So you can solve equation 2 as long as g is continuous. No matter how nasty that function is, you just might have to write this kind of thing down. So disadvantages, I think, are obvious. In practice, you might not be able to do much. You might just have to stop here and say, I don't know, shrug. So whenever you have integrals with fractions in them, that's pretty dicey. So a natural question to ask is, well, can you give me a method that like always works without guesswork and also is easy? And the answer is no. Sorry. Life involves trade-offs, So no, there's no method that like takes both advantages of both methods and avoids the disadvantages. So finally, here's a kind of question you might see in your homework or on an exam. You're supposed to be able to recognize when each method would be of use or neither of them. So for this list of DEs here, I could ask you, don't solve this. Like, don't try to solve this. Just tell me if you were to solve it, which method would you use? Undetermined coefficients, what we just did, or neither. So you can pause the video here if you want and see what you would say, but since you're not here, I will just walk through these. This function here, its derivatives don't look enough like itself. This is not a polynomial. It's not an exponential. It's not trig. This root means it's kind of out of bounds for undetermined coefficients. So this is a variation of parameters problem. By contrast, this looks a lot like what we did in section 3.5. You just have a cos over here. So this is undetermined coefficients. This one here, if you shift the 13y over to make it look like this, you would have a 0 on the right-hand side. And now you're back on your first exam. You don't need either method here. So this is a big old neither, because you don't have a free-floating t function. So parameters, undetermined coefficients, neither. This one is undetermined coefficients. You have exponential times a trig function, as we discussed in class on 3.5. Undetermined coefficients is fine for that. This one here is also undetermined coefficients because you have a polynomial, a pretty nice polynomial, just a quadratic. So here's another undetermined coefficients. For some reason, I thought I'll test you on this again. This idea. See how 3 and 6 are the same? I love 3 so much, I did it again here in 6. So neither. This one, if we were in class, would raise some eyebrows. So if we were in class, I would draw this for you. So this function here outputs either 0 or 1, depending on what time it is. So between times 2 and 5, it outputs a 1. Otherwise, it's outputting a 0. So this function looks like a horizontal line at 1, at height 1, from 2 to 5. Otherwise, it's a horizontal line on the t-axis. So this function has a break at time 2 and a break at time 5. At time 2, it jumps from 0 to 1, and then at time 5, it jumps down from 1 to 0. G of t here is not continuous. And if you look at all the descriptions of variation of parameters, you need continuity. So if somebody hands you this and says, solve this, you got to shrug for right now. Right now, we can't solve this because I gave you a discontinuous function over here. So this is a neither right here, but it's a neither for a different reason than this. This function here is just this equation is so simple, you don't need the method. Like we already knew how to do this before. This is too complicated actually for variation of parameters. Even though, by the way, this function here, just outputting a 0 or a 1 and nothing else, that, if you ask me, is actually a pretty simple thing. It just happens to be discontinuous. This function here is much simpler than like this, or cosecant, whatever. Oh, and by the way, cosecant is also not continuous, but if you read this example in the text, they say that t lives between negative pi over 2 and pi over 2 or something like that. So we were solving this where cosecant was continuous. So there's no trickery there or something. So if you want to solve this over the entire t line, you're going to have to deal with these breaks at 2 and 5. And finally, this one here is variation of parameters because there's a log right there. So having a log against the sign with the sign as opposed to an e to the t makes it just much more complicated because derivatives of logs are not themselves logs. You get like a 1 over t and then like a 1 over t squared negative. So anyway, okay, so now we've come to the end of section 3.6. I claim that we've covered how to use variation of parameters, and we've covered when it's appropriate via this example. Okay, so I will see you on Friday.